Thanks for joining us today, everyone, for this session of our HACC Tech Talks series. My name is Tom Papatheodore. I work as part of the AMD University program. For those of you who might not be familiar with this HACC programs or Heterogeneous Accelerated Compute Clusters, this is a program that's a special initiative to support novel research in heterogeneous accelerated computing for both AI and HPC. There are several HACC sites that are located around the world, as you can see here on this map. And each of these sites has compute nodes, clusters with compute nodes that have AMD EPYC, Instinct, Alveo, and Versal hardware. And the researchers who are participating in this program, they can access these clusters remotely to perform their own research. And so if you are a researcher who's interested in this type of very heterogeneous computing, then you can click this link down here below to learn more about how you might be able to participate. Also, if you're not familiar with the AMD University program, we are a technical group that sits within the Research and Advanced Development Organization, AMD, and we work with academics to help enhance their teaching and learning experiences and advance state-of-the-art research on our platform. If you want to learn more about the AMD University program, you can click this link below. So getting to today's session. So we have two 30-minute talks today. These will be focused around the Instinct GPUs from the hardware that I mentioned previously. So I will be giving a talk on the ROCm ecosystem and HIP programming. And then we're also joined today by Giacomo Capodaglio, and he works in the AMD HPC Solutions and Performance Analysis Group under the Data Center GPU organization, and he's going to talk about the profiling tools that are part of the ROCm suite. Okay, this is a session overview here for my session, anyways. I'm going to give a background first, and then we'll talk about some basics of HIP programming. Look at how you can translate CUDA to HIP using Hipify or Hipify. We'll talk about, I'll sort of briefly mention about the AI on ROCm and what the support is there, and point you to some additional resources. I should also point out that, these are 30-minute talks, so these are meant to be more informational rather than, a full tutorial where we'll cover all of these topics. So, we do have plans for actual tutorials with hands-on sessions that we'll be able to offer in the future. Okay, so for the background, I wanted to just point out the stats here of these MI210 GPUs. These are the GPUs that the folks at these HACC centers currently have in their clusters. So for high performance computing, your traditional modeling and simulation workloads, these GPUs have a peak performance of 22.6 teraflops in FP64 or FP32. And for AI workloads, using the tensor cores, for FP16 and BF16, they have a peak performance of 181 teraflops. 64 gigabytes of high bandwidth memory is the capacity on each of these GPUs, and that can be accessed at speeds of up to 1.6 terabytes per second. Looking at the communication up here, we can see we have these four MI210 Instinct GPUs, and they have this plate here. And this plate, this is the Infinity Fabric or XGMI bridge card that connects these GPUs in an all-to-all. So each of the MI210 GPUs have 150 gigabytes per second of peer-to-peer communication bandwidth, and that's unidirectional. So it's actually 300 gigabytes per second since you can overlap both directions at once. And these GPUs are connected with PCIe Gen 4 to the CPU, so speeds of up to 32 gigabytes per second unidirectional. And I have a link here for the white paper as well, if you're interested in learning more fine-grained details about the architecture. This is a MI210 node diagram, and this is really just to show that 150 gigabyte per second, what exactly that means. That's into and out of each of these MI210s, right? So here you can see when you have this, this quad all-to-all here with these GPUs, you have these 3 links, right, coming out of this particular GPU. So that's the, these are each 50 gigabyte per second Infinity Fabric links. And so you have 3 of those. And so that's using all 3 or all of the 150 gigabyte per second bandwidth into and out of this GPU. And so this is, an idea of what this might look like. Okay, so ROCm. ROCm is an open source software stack for GPU computing. This is both for HPC and AI. We can see over here on the left what this stack looks like. So at the bottom, we have our actual hardware, right? So you have your AMD Instinct, Radeon, or Radeon Pro GPUs. You're running an operating system on your server. And then you have ROCm that sits on top of that. So ROCm consists of runtimes. So these are runtimes for ROCm as well as HIP. Compilers. So the compilers, you have HIP-CC, which uses Clang under the hood. We have tools that are available, like our Hipify tools that lets you translate from CUDA to HIP. Things like the debuggers, ROCm SMI for querying the hardware, as well as the ROCm profilers that Giacomo will be talking about in the next talk. And then you have your libraries. So these are things like your primitives and your math libraries, so linear algebra, sparse solvers, FFTs, these sorts of things. Communication, and then your machine learning and computer vision libraries as well. And so then on top of this, you have the frameworks that you can use. So things like PyTorch, TensorFlow. I'm actually not sure why this doesn't say other applications, but when you build applications yourself with something like HIP, then you can this would sit on top of this as well. And this is all powered by the Heterogeneous-Compute Interface for Portability, or HIP. And so this is a C++ runtime API in kernel language. And so this allows developers to write a single source code that can be used on both AMD and NVIDIA GPUs. So HIP is open source. It provides the APIs that I just mentioned. It is syntactically very similar to CUDA. So most of the CUDA API calls can be converted in place by simply changing CUDA to HIP. So if you're familiar with CUDA programming and you have a CUDA mem copy, this would simply be a HIP mem copy in HIP. Right, and so there's HIP has supports a strong subset of the CUDA runtime functionality. And over on the right, we have this sort of cartoon view of how this works. You write your program in HIP, and then depending on which platform you're on, you would use the different backends running on an NVIDIA system with CUDA or an AMD system with ROCm. These are some of the HIP API calls that we have here. So these are things for instance, device management, memory management, streams, which are sequences of GPU operations that are carried out in order in a particular stream. Events, these are you can drop these into the streams to be able to do things like timing your code or synchronizations. Then you have your device kernel launches as well as device code and error handling. So if you're a CUDA programmer, then looking at these probably all look very familiar. They just have HIP in them instead of CUDA. And if you're not familiar with GPU programming at all, I wanted to just add in a couple of slides just to show sort of the basic ideas of GPU programming, where you have 2 separate processors. So you have your CPU, which is often described as the host, and your GPU, that's often described as the device. And so each of these processors has their own physical memory, right? So the CPU has the DRAM for the system memory. And the GPU has HBM for high bandwidth memory, or possibly DDR6 if you're talking about Radeon. And so in order to solve problems cooperatively using these, you need to be able to pass data back and forth between these. And so in between these different memories here. So the host code is your typical C, C++ syntax that you can use. You have your entry point that's main. And you can use those HIP API calls to do things like we saw on that previous slide, right, with memory management, launching kernels and so forth. And then on the device, the GPU functions that you write are called kernels. I know that's kind of an overloaded term, but that's what these are called here. And this is a C-like syntax, and this is for writing the actual code that'll be performed on the GPU. This is sort of a cartoon view of the host device programming model that I mentioned. Having the separate physical memories, you need to be able to pass this data back and forth. So, for instance, if you're running on the host, right? This is your main processor that you're running on that sort of drives the application. You allocate some memory, initialize those values, and then you want to perform calculations on those values on the GPU. Then you need to transfer the data over to the GPU, since the GPU doesn't know about those values that might have been initialized on the CPUs at this point. So you transfer the data over to the GPUs, and now you can perform your calculations that you wanted to do. You get your results back, and you pass those to the CPU. You continue on the CPU until you reach some compute-intensive region of the code that, again, you want to offload to the GPU. You send the data to the GPU, perform your calculations, get your results, send them back, and so forth. So this is a sort of naive or maybe just very basic view of this. You can actually overlap CPU and GPU computations. You can have, multiple streams of GPU operations running on a GPU and so forth. But this is the basic idea that you need to be able to manage this, the fact that you have these separate memory spaces, or these separate physical memories on these devices. This is showing the grid hierarchy that is used in GPU programming. So you have a GPU kernel or function that you want to run on the GPU. And when you launch this kernel, a grid of thread blocks is launched that has some number of thread blocks and threads. And this is how the problem is broken up to be run on the hardware. So you have this coarse-grained parallelism where it's the thread blocks, and then within the thread blocks you have some number of threads. Here I show 4 threads inside of each of these thread blocks, but that's just to make it fit on a page like this. Typically you have more than that, say 256 threads in each one of these blocks. But this kind of just shows a cartoon view of what's happening. And those threads within the thread blocks, this is your finer grained parallelism. And these threads can cooperate that are in the same thread block to do things like accessing the same shared memory, L1 cache, and be able to perform block level syncs. Down here in the bottom right, I have a table. I'm going to use the terminology that most people use, which is this NVIDIA terminology, where you have this grid, thread block, and threads, like I've shown above. I didn't mention what a warp or a wavefront is yet, but I will do that on the next slide. But I did want to point out that there is different terminology that can be used for AMD. So sometimes you'll see work group in place of thread blocks, and wavefront in place of warps. Okay, so why do we have this this hierarchy of threads and thread blocks instead of just having a bunch of threads spawned? And that's because it allows a natural mapping of the kernels to the hardware. So if you look at this diagram up in the top right of a sort of a cartoon view of a AMD GPU, you can see that you have these shader engines, these SE0, SE1, and you can see these ellipses down here, and that just shows that there would actually be more of these shader engines. But just to fit it on the page, I've only shown 2 of them. And each of these shader engines has a workload manager and also some number of compute units. And these compute units, this is where the computations actually happen. So if you look down at this diagram at the bottom, this shows one of the CDNA2, which is the architecture of the MI200 series GPUs. And this shows the compute unit. So on it, you can see what I sort of mentioned previously, which is that you have this LDS, or this local data share. This is your shared memory. You have your L1 cache, and you have your matrix and shader cores. And so these are the resources that are on one of these compute units. So the way that this actually works is that when you launch your kernel, you send this packet over to the command processor on the GPU, and that packet contains information about things like the grid hierarchy, right? The number of threads per block, the number of blocks in the grid. And so it can, you break up your problem into some number of these thread blocks. So if we assume a thread block size of 256, maybe what would happen is you would send these thread blocks off to these shader engines, and they would be dispatched to these shader engines in a round robin fashion. So thread block 0, thread block 1, thread block 2 down here, 3, 4, 5, and so forth. And although I've only shown 2 thread blocks here, what would happen is, when you dispatch these in this round robin fashion, you would fill up these shader engines with these thread blocks that would then be computed on these compute units. And so the part that I didn't mention previously about the wavefronts, or the warps, because of the SIMD units that are on these compute units that are 64 wide, you break the problem up even further. So these thread blocks are then broken up by the workload manager into these warps, or these chunks of threads that are called wavefronts or warps, and then those are mapped onto the compute unit. So here we have this thread block 0, and that gets broken up into 4 64 wide chunks of threads, and then those get mapped to the compute units, and then the compute units work on these wavefronts or warps on these SIMD units. And so you're not actually processing the thread blocks as a whole. Instead, you're breaking it up into these chunks. And the reason that these all get mapped onto the same compute unit is that what we mentioned previously, that these compute units have these shared resources. And in order for the threads within a thread block to cooperate and solve a problem together, they all need to have access to these same resources, right? The shared memory, the L1 cache, and so forth. And so because of this, these SIMD operations and the fact that these are 64 wide, it's important to make sure that when you set your number of threads per block, that you do so at a multiple of 64, so that this can get broken up into these 64 wide chunks to be performed on these SIMD units. Okay. So now let's see how this actually works to make this more concrete with HIP program. So we'll use a basic vector addition program for this. This is the hello world of GPU programming here. And for this, we're going to need these 3 HIP API calls. So you can see that each of these HIP API calls has a HIP return status. And that's something that you can check the value of to know if you were successful, and if not, what the error might be. So for HIP malloc, this is analogous to a normal like a C malloc. So you pass in a pointer to a GPU buffer, and then you give the size of the GPU buffer in bytes that you want to create, and it allocates that for you. For the data transfers, if you want to transfer data to or from the CPU to the GPU, then you can use this HIP memcopy. The arguments are as follows. So the second argument, this is the source of where you're transferring the data from. And then the first argument is where you're transferring the data to. So I always look at this memcopy call as transferring data from here to here. Whenever I look at this, you can set the size of the buffer that you want to send in bytes. And then this last argument here shows the direction of transfer. So you're transferring data either from the CPU to the GPU, so that would be host to device, the device to the host, or device to device. And when you want to deallocate the memory, you can use HIP free and just pass in that GPU buffer. Okay. So this is a full vector addition program that we'll take a look at here, just to walk through. So we did include our HIP runtime up here at the top in our include statements. This is our GPU kernel function. We'll look at this after we walk through this full code. We'll look at this in more detail. But for now, know that that's just the code that will be offloaded to the GPU. So this is the beginning of our main program and the end. So this is just C programming. Here we're setting the number of elements of our array and the number of bytes in the array. We allocate memory on the CPU. And I like to prefix my variables with an H underscore when they're for the CPU or for the host. That's just a convention I follow. You can use whatever you want. We initialize the values on the host here. So I'm simply setting A to be sine squared and B to be cosine squared, so that when I add these together, all the values in C will be 1, for an easy way to check. And at this point, yeah, this is all just CPU programming, right? Your normal C. And the values live in DRAM. So in order to then offload to the GPU, we need to make down here an analogous set of these A, B, and C buffers on the GPU, which I've prefixed with a D underscore for device. So now we've allocated memory on the GPU. And here we're sending data from these CPU buffers to the GPU buffers, right? Because we've initialized the values. We need those values to live on the GPU, so we send them from the host to the device. And we can see that we've set this to host to device over here. Now that the data lives on the GPU as well, we can launch our kernel. So we set our number of threads per block, and then we calculate the number of blocks in the grid based on the number of elements in our array and the number of threads per block. We use the ceiling function here to make sure that we, if we don't divide evenly, that we make sure we have enough threads to cover all the elements of the array. And then we launch our kernel, and we'll look at this kernel launch after this, along with the GPU kernel itself. Once we've completed our GPU kernel, we then send the data, the results, back from the device. Now we have a device buffer here in the second argument, and we send it to the host. And you can see that we've changed this to be device to host, as opposed to host to device above. And then now that the data is back on the CPU, the results, we can check the results to see if, check for correctness. Free our CPU memory, free our GPU memory, and print success if we finish this successfully. Right, and then as promised here, we have the HIP vector addition kernel. And so let's take a look at what this consists of. So we have this global keyword here, and this indicates that this is a HIP kernel function that can be launched from the host or the device. This has a type of void because HIP kernels do not return anything. We've named it vector addition. You could name this whatever you want. These are our arguments to the kernel. So these A, B, and C, these are expecting GPU buffers that we've allocated with HIP malloc, as we saw in the previous couple of slides. N, that's just the size of the array, passed as an integer by value. And then you'll notice that inside of this kernel function, there's no for loop, right? Like you might have on a CPU when you're iterating through all the elements of an array to perform a vector addition. And that's because each of the cores, which have a thread running on them, one of these GPU threads, each perform one of the elements of the array. So you don't have this loop. This line here defines a global thread ID based on the particular threads, thread index within the block index within the grid, and the number of threads per block. So that can define a global thread ID that you can then use to perform that thread's element-wise addition here. And we have this if statement here to guard against going outside of our array bounds. So I mentioned that you might have more elements, or I'm sorry, more threads in your grid than you have elements in your array to make sure, if things don't divide evenly. So you just need to make sure you're not stepping on memory that doesn't belong to you. Launching a HIP kernel. So this is how you launch this. We use this triple chevron notation here. So you have a kernel name. And down here, you can see we've called it vector addition. This is the number of blocks in the grid is the first argument. So we plug in our blocks per grid there. Threads per block is the second argument that we plug in here. And you'll see there's these two optional arguments as well, which I've not used. Those are both set to 0 if you don't define those. And these are the number of bytes of shared memory. And so that's for dynamic shared memory. And the stream ID that you can use as well. And then you have your actual arguments that we looked at in the last slide that you pass in to the function. It's important to note that when you launch a kernel in this way, that execution is given directly back to the CPU. So these GPU kernel launches are asynchronous with respect to the host. Once you launch this, the kernel gets launched on the GPU starts churning on whatever it is that you're doing, but the CPU just continues to move forward with the program unless you put in a barrier or something if needed. I might pause here and see if there's any questions that anybody has at this point. Feel free. I think you can unmute yourselves. If not, you could post that in the chat, and I'd be happy to answer questions as we go. Okay. So we'll look at some CUDA to HIP translations here. So these are ways that you can transfer your CUDA code to HIP. Here we have this HIPify tool, and so you can use it to translate your code. And so here you can see if I put in this -examine flag, it'll show what would happen if we ran this HIPify Perl script on a vector addition code that is written in CUDA. And you can see that it shows you how many references it converted from CUDA to HIP in 107 lines of code. So it did things like 3 instances of converting CUDA free to HIP free and so forth. And then when I want to actually perform this translation, I like to pipe it into a separate file here, which you can give either a .cpp or a .hip extension. And then once this is done, you can then compile this with the HIP-CC compiler driver, and then run your program, convert it into HIP on the program. So I should point out that this is only going to recognize CUDA calls. It's not going to translate things like comments that might say CUDA in it, or if you have user-defined variables like my CUDA error variable or whatever, it's not going to translate those. It will give a warning if it sees references to CUDA that it doesn't recognize, it'll tell you, hey, I found these, I didn't translate them, but those are things you would need to go back in and manually change. So what I typically do now, since I've started working with both AMD and NVIDIA GPUs, is to always just use something generic like GPU instead of CUDA or HIP. And down below, you can see some documentation on these tools. There's another way that you can do this. If you have CUDA source code and you just don't want to translate that to HIP for whatever reasons, you can leave your code in CUDA, and you can use this header file method or this HIP-apply method, where you can define a header file, as you see over here, where you define CUDA malloc is HIP malloc, CUDA memcopy is HIP memcopy. And since the call structures are the same, this will sort of ephemerally do your translation from CUDA to HIP, but you don't need to actually change your source code other than adding in this header file and then being able to add include statements into your CUDA files. And so then you can compile and run this, leaving your source code in CUDA. So AI on ROCm. So I think we've covered a lot of what I've shown here. This is really just showing sort of the support. And again, it shows this software stack over here where you have these frameworks running on top of it, and then your models over here. So not only can you use things like PyTorch and TensorFlow as you would normally on NVIDIA GPUs, but you can also use some of the higher level tools like for LLMs, right? You have Hugging Face models, or being able to use, say, Llama CPP or Ollama. These are all supported on the system as well. And so, yeah, you can take a look at some of these AI ecosystem partners down here. But I'm going over my time here, and since we started a little late, I'm going to move on and just point to some additional resources. So I have just showing here how to install ROCm-enabled PyTorch if you're the type of person that wants to not use maybe a system level install of this, but want to have a virtual environment and install in here. This can be done simply using wheels. And then here we have just some additional resources on our latest architectures for CDNA 3, RDNA 3, and I point down here to some resources. So HIP documentation, these great AMD lab notes that show optimization techniques and sort of used as self-guided tutorials. And similarly for AI, these ROCm blogs are really great to look at these self-guided tutorials for all kinds of AI-enabled workloads on AMD and ROCm. Okay.